Okay. Can we start?
Yes.
Okay, then welcome everybody to the ISCOWA webinar. I would like to apologize for the slight delay, but we are now ready to start. So my name is Katrien Scholbach. I'm a researcher at the Eindhoven University of Technology in the Netherlands. I'm also board member of ISCOWA, and it's my pleasure today to invite you to this webinar and moderate it. So for those of you who do not know, ISCOWA is the International Society for the Environmental and Technical Implications of Constructions with Alternative Materials. We're a non-profit organization that was founded in 1991, and as a group we try to promote the use of industrial byproducts in construction and contribute to the circular economy in this way. And I'm very happy today to welcome Professor Kinnunen from the University of Oulu in Finland as a speaker. So Professor Kinnunen leads the research group for magnesia-based materials and systems, and he has a special interest in carbon storage and capture, which will also be the topic of today's talk. So please, Professor, go ahead.
Thank you. So let me share the screen. Okay, so let me start. So yes, I modified the title slightly into towards carbon storage and construction materials, and I will start with the bit of introduction to our group, and then to the topic in general, and then at the end I will show some specific results from research. So I'm leading this research line called Inorganic Circular Materials at the University of Oulu in Finland, and it is under this fiber and particle engineering research unit. So get a pointer out. So we have 4 professors, 2 senior research fellows, 9 postdocs, and 28 doctoral researchers. So quite a big group, and mainly the funding comes from external sources, from different projects from EU and Business Finland and so forth. And in terms of topics, we are looking at basically inorganic side stream utilization, as one main theme, and then construction materials, concrete, cement, and then also high-end applications of geopolymers such as water treatment. And then my own group is about 10 people, and we're specifically looking at this magnesia-based binders and their carbon mineralization, which will become clear in a moment why that is relevant to, or why magnesium is especially relevant. And there, in addition to laboratory work, we also do different kinds of modeling, so thermodynamic modeling and atomistic modeling, and also LCA. So in terms of the University of Oulu, it is really multi. There's many different fields that we research, and we are working under this green transition and circular economy. These are focus areas of the university, and so it is well also received at the university level. Okay, so let me start first with the bigger picture. So here's the planetary boundaries framework, where we have different boundaries that have been found and also found to be exceeded. So there's, for example, biochemical flows, phosphorus and nitrogen, which are well into the red, and red here is the high risk zone. And then there's something that we're working on directly, which is the CO2 concentration, which is on the red, but not as badly. But also land system change, which is something like if you're working with waste utilization, you can recover those those areas that are used for landfill. So this is the issue that we have, and this is here to point out that the issues that we have are really multidimensional, and we have to keep in mind that any solution that we propose tend to have side effects. And actually all of these risks that we currently have are results of side effects of previous technologies. So we have to be really careful in thinking about technological solutions to the problems, because what tends to happen is that as researchers, we tend to simplify the problem so that we're not actually looking at the whole problem, but we simplify it and then we find a technological solution to the simplified problem, which is not actually the problem itself, it's our simplification of it. And this is what many times happens, is that we think about CO2 concentration and we just focus on that. And that is exactly the wrong way to do it, because that will only increase different side effects down the road. And so this is not a sustainable approach. So what I'm proposing here is that we have to start thinking much more multidimensionally and start to take into whole system into account. How do we actually solve the issue and not just look like we're solving the issue? So there's a reminder for that. Okay, so emissions in terms of concrete are shown here. And CO2 emissions here at the bottom. So this is basically starting materials, and then the material flows, where do they go? Then we have construction in stock and end of life management. And in terms of the CO2 emissions, bulk or almost all of it, not quite, but most of it by far comes from the cement production, and not from the stone production, even though that's 90 or 80-90% of the mass or volume, but it's from the 10% that's cement that causes over 90% of the emissions. So clearly, if we want to reduce CO2 emissions in cement or in concrete or construction, cement is one of the main issues to look at. And so here's carbon cycle shown, and we have actually two kinds of carbon cycles. We have a short cycle and or slow cycle and fast cycle. So the fast cycle is something like, let's say, hundreds of years. And that's CO2 going from the atmosphere to land or to ocean and back, and that takes, like I said, something like hundreds of years. But then we have actually much bigger cycle, a much slower cycle, which is the slow carbon cycle, which is you can see the gray big arrows. And that is actually carbonates going into minerals. So here I have calcium carbonate. So it's sedimenting and forming these sediments, and this actually takes hundreds of millions of years. So it's much slower, but it's also much bigger. Over 99% of all the CO2 is actually in minerals on underground or on the ground. And only trace amounts, if we look at the composition of the atmosphere, there's only 400 parts per million CO2, which is trace amounts, very small amounts, but it is so you can see that it's very easy to increase the CO2 levels by orders of magnitude in the atmosphere if we're not careful. And so some of the major reasons are the fossil fuels and cement production, this outflow. And basically, you can think of it as increasing the slow cycle, this arrow up, and of course then if we don't at the same time increase the down arrow, what will happen is that the atmospheric CO2 concentrations will go up, and that's what we're seeing. So you can represent it like this. So we have starting material, something like calcium carbonate. For cement, this is the major raw material, and you end up, this is a simplified system now, so you end up with CO2, which is a gas, and then you end up with the calcium oxide, which is a solid, and then you also have, in the case of cement, you have silica there as well. The thing to note here is that that we all know that Portland cement is a really good material in terms of mechanical properties and durability and everything like that. And it's also really cheap and requires low energy to produce. This is of course why it has become the main binder by far. And so the amount of energy needed is about, in theory, about 1.5 gigajoules per ton. Which is little. So if you compare that, if you take 1 ton with the same amount of energy, you could take 1 ton of water and heat it up to around 250 degrees. And with that energy, you can actually produce the cement. So it's very very little in terms of energy, and so this is what we're up against. If we want to come up with alternative binders, it needs to be better pretty much in every way compared to this. So especially in terms of energy, it needs to be at least comparable. And of course, in real system, it's something like twice this. So 3 gigajoules per ton is something. Let's say 4 is what the current industrial standard is. So okay, so this is the current situation. So we're putting CO2 in the atmosphere, and actually, if you look at in terms of grams, this is about the same amount of CO2 or calcium that's produced in this reaction. So you can think of CO2 as being one of the end products, one of the main products that in the cement production. It's just that it's invisible, so that we don't see it, and that's why we have been able to do it for so long without realizing it. So what we have to do then, in order to, or what we could do, let's say, in order to reverse this, or at least mitigate it, is that we could do something like a reverse reaction, where we take an oxide and react it with the CO2, so that we get a stable mineral. And unfortunately, you cannot do this. Well, let's say you can do that with with calcium oxide. It's just that calcium is as calcium carbonates in the crust. So if you have a source of calcium oxide, if it's a large-scale source, it is in its history, it has been first calcium carbonate, and then it's been decarbonated. So this is why taking any waste calcium oxide is very important that we do that, but it's not actually doing what we think it does. It doesn't actually close the cycle, the full cycle, if you think about the slow carbon cycle. So if we want to speed up the big arrow in the carbon cycle, what we have to do is take magnesium silicate. It's the most straightforward alternative to calcium, and it exists as magnesium silicates. And there, what you can do is you can separate the magnesium silicon, and then you can, once you do that, I have the energy here. So the theoretical energy is 0.9 gigajoules per ton to get magnesium oxide from magnesium silicates, and you can see that that's maybe about 2/3 of the value for calcium. So far, so good. We have an option, an alternative that is actually carbon storing, because we can take the CO2 here, react with the magnesium oxide, and end up with magnesium carbonate. And this whole process, these two combined, is called mineralization. And so the next step if we think straightforwardly, is that, okay, if we first mineralize it, so maybe a little bit of background, I will go more into detail in the mineralization, but here it's just mentioning this is mineralization, and if we want to then utilize it, this is a powder. This magnesium carbonate is a really fine powder. It's like pretty much like dust. The particle size is about 1 micron. So it's really difficult material to work with. And the main question then, if you want to utilize it, is how do you increase the particle size, or how do you bind it together, basically? And there's, I guess I don't have a citation here, but this is from a science publication about let's say a month or two ago, and there they looked at all the different carbon storage, or all the potential materials for carbon storage, and you can see here that the aggregates for this accounts for concrete aggregates and bricks, cement, and cement filler are the biggest, and then you have others which include something like fillers for plastics and paper and things like that. But you can see that by far the biggest application is in aggregates or bricks or cement. And the carbon storage potential of those materials is actually quite large. It is about, I guess, if you combine those, it was something like 16 gigatons per year of CO2, and this corresponds to something like a third of all the CO2 emissions on the planet, of all the anthropogenic CO2 emissions. So in terms of the volumes, the volume would be there for aggregates or bricks, or let's say construction materials in general. Energy is low enough, volume is there. Then the next question that could be asked is that, okay, what about the raw materials? Is there enough raw materials to do this with this proposed mineralization and utilization route? So one of the motivations for our group, actually, for the past 10 years has been this. There's a lot of big mineral waste streams in Finland. There's mining waste as the biggest, and there's magnesium silicate containing mining residues, or mine tailings, as they're called, which are already finely ground, which are the sort of prime starting material. And here I've also put the CO2 emissions, so and they are about the same volume. And so it turns actually out that that there are enough magnesium silicate sources around the globe, and they're quite evenly distributed. So this is not an issue. So then another question that that one has to then ask is that, okay, if we are going to make take this powdery material and make that into some kind of construction material, you have to have some kind of binder that you bind those together. And so we have been working with well, Portland cement, but also different kinds of alternative cements, geopolymers, etchingite-based binders, but also carbonate-based binders. This is actually missing the hydrated magnesium carbonates that you can also use. So those are the different sort of minerals that you could, in theory, turn into binders. And let's look a little bit later more into that. There's actually, it's missing a lot of magnesium-based binders, such as magnesium silicate hydrate, that we'll return to. But here, just to return to the availability of the minerals. And so here we have global CO2 emissions on this bar, and I've plotted against the y-axis so you can see more clearly. And so we have axis here, and you can see that there's the difference between the next. Let's see, we have seawater and so forth here, which are a little bit more difficult sources. But then we have magnesium silicate rocks, magnesium and calcium silicate rocks, and then brucite. And then here we have different waste streams, and you can see that the waste streams are actually 100 or even 1,000 times too small in order to address the whole of the problem. Maybe we don't have to actually address the whole global emissions, but still, even if we want to do half of that, it would still be 50-fold difference. So we can see that there's a problem in the sort of mainstream narrative in using just waste streams. But then there's also good news that you can see that the magnesium and calcium silicate rocks are abundant enough by far to address the problem, and actually also seawater brine. But there's an additional sort of energy requirement that needs to be taken into account. So calcium silicates actually don't exist in that big volumes. You do have a mineral called wollastonite, but that's very rare, and so it cannot be used for this purpose. But you do have a lot of magnesium silicate rocks, and there's also basaltic rocks which have both magnesium and calcium. But calcium is much easier in terms of chemistry, and so that doesn't require so much research. The problem seems to be with the lack of knowledge in terms of magnesium currently. So here actually plotted those magnesium containing silicates. So there's basalt and then anorthite, and then magnesium-based ultramorphic rocks, serpentine and olivine, and you can see that these are quite evenly distributed. Maybe not as evenly as calcium carbonate, but still quite abundant enough. So then here's one proposed way of utilizing these mineralization wastes, and so this is from the literature. So you have your mining, your limestone. So this is your calcite or your OPC feedstock. So you're mining that, and then you're using conventional cement plant. And then here, what it envisaged here is that you mine magnesium silicate, and then you get the CO2 from the cement plant to mineralize that, and then store that magnesium carbonate in another mine. And then you take the silicate that's left over from the magnesium silicate, and then you make a cement mix out of that. And that's fine, except that this is not environmentally that viable. Like I said, this is a really dusty powder, and you're unlikely to get environmental permits to do that. But in theory, this could be done. And so what we're then trying to do is that, okay, how do we take also this magnesium carbonate waste and introduce it also to the cement or to the concrete? Maybe I'll just mention here that in our preliminary results, the hydrated magnesium carbonates are quite reactive, but they seem to react negatively in the cement reaction. We are preparing a publication on that. Right, so it's not as straightforward as I just mentioned. But here, if we just look at the sort of volumes that are possible, so if our aim is to use magnesite as aggregate, so we could take, in theory, the magnesium carbonate aggregate, and then we would store something like 900 kilos of CO2 per cubic meter, and then we have the Portland cement, and then we could add magnesite as supplementary cementitious material, but that would result in much less CO2 reduction or storage in this case. So you can see that by far the most of CO2 will happen, what storage potential is in the aggregates. And so this is why we're thinking about that. And also there's a way to, well, actually, let me just skip ahead for a little bit. So here, pretty much the same thing that just to reiterate is that in the current paradigm, what we have as the feedstock is calcium carbonate. We produce calcium oxide or clinker containing phases. Clinker phases containing calcium oxide, and then we emit CO2. And then in the reaction, what happens is the hydration, is calcium as pearlandite and other hydrates. And then you can, in theory, carbonate that, and this is what's done, for example, in the demolition waste carbonation. You can take some of the CO2 back, and at best you can have zero CO2 here, and actually, because you're not carbonating all of the calcium, it's quite much less. But then this is sort of inviting us to think in a slightly different way, which is that if we start from calcium magnesium silicate feedstocks, and then we produce calcium oxide, magnesium oxide, we need energy, but not CO2. We don't emit CO2 from the chemistry perspective. And then we can do carbonation, and then we could end up with the calcium. This is basically dolomite. And at best, we could there reach something like minus 1,000 kilograms of CO2 per cubic meter. So this is just in theory, but you can see that there's a big difference, and the question is that possible? One more slide about that, which is, this is already old slide, but this is showing market size in terms of billions of euros in the y-axis, and then year, the x-axis. And so here you can see that the biggest market size for greenhouse gas mitigation potential would be concrete, and the mitigation potential would be in the order of 2 billion tons of CO2. But then the same story as earlier here is that aggregates are much bigger in terms of the storage potential. Actually, according to the more recent paper, it's something like 3 times this. But what's also evident is that the market size is much smaller. And of course, we also have to take into account that this aggregates are the cost of aggregates are the reason for using aggregates is precisely because of their low cost, and so it's only some euros per ton of materials, and usually the transportation becomes an issue already after, let's say, 50 kilometers. So it is not as simple as just replacing the material. Okay, so then let's shift the angle a little bit and look at the carbon mineralization. So carbon mineralization is a field in itself, and it's a completely separate field from cement and concrete. And so what we have done is sort of we're sort of working on both of the fields, and so now I want to also bring to your attention also the perspective from the carbon mineralization point of view. So here what essentially is done is that you can get you have the minerals here, serpentine, olivine, or wollastonite mentioned here, or you can have industrial solid wastes, and you have CO2 from waste, or you can also have direct air capture where you get the CO2. And then what's called ex situ carbon mineralization plant, which means that you're doing that in a process, in the external process. You have also in situ mineralization, which means that you're doing that underground, and then you don't get any product out of it. You're basically pumping CO2 underground, and that reacts there to make these same minerals. And that's currently that's carbon. It's called carbon capture and storage, and that's considered the most feasible at the moment. Although it does have big question marks in terms of what happens to the CO2. You have to have long-term monitoring on site and so forth, and we don't have that long experience using it. Anyhow, what you get here is that you only you don't get paid for the end product. And of course, when you're doing ex situ mineralization, what the good thing is that you do have this side stream or a waste stream that you get from the mineralization, and that could be sold as a product. And so that's their perspective, is that the biggest question in the mineralization, in the ex situ mineralization, is what do you do with the end products? Okay, so a bit of the chemistry here. So depending on which starting material you have, but you have the carbon dioxide converting it to carbonate and then reacting into different carbonates. So this is either magnesium carbonate or calcium carbonate, or a mixture of those. And so if depending on what temperature and pressure you do that, you end up with either hydrated magnesium carbonates or with this here's unhydrated, which is magnesite. And this magnesite is a thermodynamically stable end product and is favored because of that. But then you need higher temperatures and pressures in order to achieve that. Okay, so this is the carbon mineralization, and like I said, in the ex situ carbon mineralization, the biggest question is what do you do with the end product? In terms of the sort of technological readiness level, it's still not too far. Maybe it's TRL 4 or 5. Maybe could be up to 6 currently in terms of the magnesium, and the cost is somewhere around 50 euros per ton of CO2. So it's not actually that bad in terms of the costs, because you have to remember that you can also get if you do use ton of CO2, you can get credits for that. And currently the cost of the carbon credits is about 100 euros per ton. And so it would already be covering the processing, but what it doesn't cover is what do you do with the end products. And this is of course why the calcium carbonation is all the rage at the moment, because it's easy to turn into construction materials. Calcium carbonation happens quite fast, and it's already quite well understood. So this is already underway, and there's a lot of startups doing that. Here, so okay, just to go back, so in terms of the mineralization, industrial scale mineralization plants, if you're just thinking about the carbon storage, calcium is not a viable option, like I said, alone. So it is usually from magnesium carbonates, magnesium silicates, or other magnesium or magnesium carbonate, calcium silicates, which is mixed silicate, that are considered. And here is one example about the life cycle assessment, and so you have so this is starting from zero, and feedstock supply. You have some CO2 emissions pre-treatment. So this is serpentine. So you have to heat treat it. So you get some penalty in terms of that. Then you get the CO2 off gas that you're storing into the material. Then you have to account for the CO2 supply. So you're actually capturing the CO2, which you get a penalty for that. And then carbonation also costs some CO2, as well as post-processing. But then here, what they considered is a, I guess, theoretical example of replacing cement. And then you get another substitution credit when you're replacing CO2 emitting materials. So you get this substitution credit, and then you have the take into account the factory construction. But in terms of the end carbon footprint, you end up -1, which is more than you could do in the CCS. So if you're just doing CCS, you don't have this substitution credit, right? Because there's no you're only producing waste, whether that's underground or underground. But here when you're doing the utilization, you're also substituting CO2 emitting materials, and then you get the substitution waste, and then that's why you end up in such a good CO2 balance in terms of that. I have to mention though that this is quite idealistic scenario, so this is not done with the sort of realistic numbers, but anyhow, this gives you a picture of how to think about it. Let me just skip ahead actually to the results that I wanted to present to you. So here I want to introduce you to a novel carbonation process for precast elements. And so we are taking nesquahanite, which is type of magnesium carbonate with some crystal water. Here's the equation for that, and so basically you have it here, and you have this is the source of magnesium and the source of carbonate. And then what we took here is that we took calcium-rich sources, which is there's calcium, there's silicate, and also some aluminate. And the question that we posed is that can we take this nesquahanite, where we have the carbonate, and combine it with calcium-containing sources without losing the CO2? So where would the CO2 go is the one question, and then also would we get binder out of that? And our sort of initial guess was that okay, calcium carbonate is more stable, so we guessed that okay, or hypothesized that it would go to calcium carbonate and it would stay in the system, and then MSH is also stable, so that would be the binder phase. So that was the what we came into that. And one of the major questions, or one of the major pains, let's say, in the carbonation, in the current, let's say, calcium carbonation or calcium mineralization and utilization in construction materials, is that if you have flue gas, the density of CO2 is really low. So it's actually even lower than that. It's well, no, it's something like kilo of CO2 per cubic meter. And then if you start to increase the pressure, you have the pressurized CO2, which is about 100 kilos per CO2. And so you have to, but in order to pressurize the CO2, you first have to take it out of the flue gas, then you have to purify it and then compress it. And this is actually quite expensive. So our question was that if you could start with the nesquahanite, this is the nesquahanite that we showed here, the density of the CO2 is actually orders of magnitude higher than the flue gas or even the pressurized CO2. And you can actually make, if you have magnesium oxide, you can react that directly with the flue gas. That makes that the reaction happens, the downhill reaction that happens in room temperature quite rapidly. So this is a way to avoid the first separation and pressurization, right? Because if you have to pressurize, then this incurs costs to you. So our question was, okay, what if we take this mineralization waste? Remember, this is a waste from this process. So we get these wastes that the mineralization people are thinking, what do we do with them, right? They want to desperately find ways to utilize these wastes. And so this is our question. If we take that waste and then we also take some calcium-rich wastes, and could we turn that into construction materials? And so in terms of curing, we went for this steam curing, which is just an autoclave that's showed here, that's used for autoclaved, aerated autoclave concrete. It uses about the same pressure and temperature, so it's 15 bars of 200 Celsius CO2, and for 8 hours. And this is also used for CSU bricks. And surprisingly, this is a low, quite low energy route. So it, because you can recycle the steam, and also the reactions that happen are exothermic. Those are happening at the high temperature, so you can recover the heat. So this is surprisingly good process. So, and turns out what we have is MSH. So here's the, well, I'm not going to go through here, but these are different compositions that we had. For example, here we have MASH, calcium, together with calcium carbonate, there's water, and some unreacted magnesium silicate. Microsilica. So for some, we added microsilica in order to see what would happen to the calcium carbonate. And turns out that yes, we can have coexisting calcium carbonate and MSH or MASH, and we can actually also get decent compressive strength. This is about 5 to 7 megapascals, 5 to 8 megapascals, and these are not, of course, optimized. So, so we could see that we have coexistence of even silica and calcium carbonate, and the calcite does store the CO2, and the MSH gives binding phase to the bricks or to the precast elements. And in terms of the carbon retention, we calculated how much of the CO2 actually stays in the brick and how much is leaked out. And we can see that that is almost, so 70 to 100% of the CO2 is retained in the material. And this is, of course, really good news. And just to go back into the beginning, so when you do that, you're combining, this is a solid carbonate, and you have just solid raw materials that you're combining. So it's, you can get those well mixed in the beginning, and those are the reactions are happening inside your brick, and if you compare this to carbonation processes, it's much more simpler. So like you don't have to care about your let's say the humidity level or carbon dioxide level. If you're doing calcium carbonation, it's really you have to control those variables really well. And if you're starting from flue gases, your carbonation is going to take probably days, and you're not going to get 100% carbonation. But here we can use just simple industrial autoclaves. We don't have to worry about anything about the carbon introduction, because it's already introduced in the mineralization stage. We just take the waste from the mineralization and utilize it here as a source of carbon dioxide and magnesium, and turn that into a binder of MSH and store the CO2 in the calcium carbonates. So that was my presentation. So I would like to thank my team who has all the expertise to do these experiments, and also, of course, the funding bodies that have funded the projects that we're working with. So thank you.
Oh, yeah. Thank you very much for that insight into your research. That was very interesting. So we do have, I think, the option for asking questions. So if you're in the audience, you can look at the top. You should have a tab for Q&A. So you can type your questions in there if you like. I should probably give the people a minute or two to type out the question. And maybe in the meantime, I can just ask you a question. Can you hear me?
Yes.
Okay, sorry. I thought I'd lost you there for a second. My question is about, have you done any research into purifying these magnesium carbonates, etc.? So, for example, like trying to remove the silica, or also, I don't know, worry about other impurities in there, like iron, nickel, etc., that could be in the olivine or the serpentinite, things like that?
Yeah, that's a good question. It's a like area of active research right now. That is not actually our like our main focus at the moment. So there's the mineralization, and then there's the utilization, right? So we're more sort of taking for granted that somebody will figure out the mineralization. We are starting some projects, but we're sort of separating those out, and we have because the first question was, can we do that even with clean materials? And so now we are getting confident that, okay, we can do that with clean materials. So the next, and also in theory, the energy requirement is low enough. So the next question is, okay, so then how do you combine those? And you are right. So if it does have nickel or let's say potassium in some cases or whatever, so you would have to take care so that you're removing the valuable and harmful elements from the feedstock, and that has to be baked into the mineralization step, and then we're then utilizing that in the further steps.
Okay, that is very clear. Okay, so are there any questions? I received a message that apparently the Q&A does not work for some reason, so then please try the normal chat. So hopefully that works. Ah, okay. We indeed, yeah, we did get a question. So the question is, I will just read it for you. So the question is, I would like to ask about what are the challenges of carbon storage in construction?
Yes, I think the major challenge right now is that we don't know much about the let's say the binding. We don't know which binders are compatible with the carbonates, because we do have to make that so that it's thermodynamically stable, so that there's no chemical reactions happening. Because what you could do is that if your pH is wrong, you could be losing your CO2 over time, for example. So that's one big issue. That one other issue is that some of the approaches that are published is that the carbon storing efficiency is really low. So you're only using, let's say, 40% of the potential, or only like 20% of the potential of the carbon storage in the material. So let's say if you're using 1 ton of magnesium oxide, but you're only carbonating 400 kilos of that. And so you're missing out on most of the potential, and this is not going to be sustainable. And so I think that those are the questions that are open. And one of the big challenges is also transportation. How do you find a place where you have access to CO2, and then you have access also to these calcium and magnesium silicates, and then how do you do the transportation so that it makes sense? I think that's one of the big challenges as well.
That makes sense. Are there any other questions? It does not seem to be the case. Then maybe let me ask another question. You mentioned it briefly that you are preparing. No, wait. Somebody raised their hand. So, yeah. So they have another question. So that is about the NQ plus calcium silica mix. Is this type of binder, does the binder need a lot of water compared to PC concrete to cast? And how long does it take to reach 8 megapascal? So very specific question there.
Okay, yes. So in Esconite calcium silica mix, is the binder need a lot of water? Yes. Okay. So So here, this is done in the autoclave, and in the autoclave, it's actually, you make the body a little bit differently. So you're making something like earth moist concrete, or even less water. So I think the water, I don't remember exactly, but it's something like 10% of the mass. So you don't have to worry about the water need that much. And then how long does it take to reach 8 MPa? So the curing is 8 hours, and this is the industrial practice right now. So if you're, for example, CSU brick is calcium silicate unit, and there you have calcium oxide with silica, which is the binder, so CSH basically, and that's an industrially viable method that's used in different countries, especially in Europe, and so yeah, I hope that answers your question.
Thank you. So anyone else? We still have a little bit of time left. If not, I will take the chance to ask my question, because you briefly mentioned that the magnesium carbonate does not work that well in cement. So because I'm curious about that, because calcium carbonate itself can be beneficial in Portland cement, but that does not appear to be the case for magnesium carbonate then?
Well, yes, so we haven't finished the study yet, so so I'm not going to say too much, but I think the reaction is that it's too reactive, or so much more reactive. So in this case, it was hydrated magnesium carbonates, and those are metastable. And so originally, if you remember 20 years ago, calcium carbonate was thought not to be reactive, right? It was a filler. It was thought to be a filler, but then people figured out that actually it is reacting, and is but the reaction is so slow that it actually was thought to be non-reactive. So in the case of hydrated magnesium carbonates, the reaction happens in some hours, right? And when that happens, that can have a major impact on the pH, for example.
Okay, that makes a lot of sense. Thank you. So if there are no other questions, then I would like to thank you again for that nice presentation. And before everybody leaves, I would like to mention that if you are interested, you can become a member of ISCOWA as well. And one of the benefits is that you receive a reduced fee for the attendance of the next WASCON conference, which incidentally will be held next year in Fukuoka, Japan. So if you are interested in that, keep an eye out. So, and of course, we will on LinkedIn and on our website post more information about that as soon as it becomes available. Okay. Then, yeah, I thank everybody. Yes, there is also the link in the chat. Thank you, John. So, yeah, with that, I would like to thank everybody, the speaker and the audience for the questions, and I wish everybody a nice weekend. Thank you.
Thank you. Bye-bye.
Bye-bye.